Welcome back, everybody. So in this video, we're going to continue our journey studying the basic building blocks of logic. So in the last video, we saw um, the simplest building blocks like negation, conjunction, and disjunction, which are just fancy words for and or. Right? But most of the proofs we're going to be writing later and the things that we need to be concerned about are not really just statements like this and this, whether that's true or not, but things that are implications. So, implications are statements like if P, then Q, right? Um, that may seem a little weird when you first say if P, then Q. Right? What is P supposed to be? So, an example might be something like if f is a differentiable function, then f is a continuous function. That's the kind of thing we're going to be talking about later. That's the kind of theorem that we're going to prove later. Um, but when we write out, you know, this in symbolic language with P's and Q's, then we usually will just say if P then Q, language like that. But that does look a little weird, and so maybe it's more helpful to think about it this way. What we're really saying is if P is true, then Q is true. Okay, because it seems like it needs a verb somewhere, right? So, so maybe the way to think about the implication here with if P then Q is really to read that as if P is true, then Q is true. Right? Another way that we'll write this and say it is with the double arrow there. So this we would read as P implies Q, right? So P with the little arrow and then Q. Okay, so what should the truth value of P implies Q be? So again, we've written out once again all of our different possibilities for whether P and Q could be true or false. And in that same order, again, there's no rule that says we have to do it that way, but it is a lot easier on everybody if we all do it the same way. So in the first row, P is true and Q is true. Okay, so what should happen? We're trying to see if the statement if P is true, then Q is true. Did that make sense? Did I pause long enough there for that to make sense? In other words, what I'm asking is the statement, quote, if P is true, then Q is true, unquote. Is that true? Well, in this case, it is, because P is true and Q is true. So if P is true, then Q is true. That would be true. Okay? What about the next one? In this case, P is true and Q is false. So what would happen to the statement if P is true, then Q is true? Well, that'd be false now, because in this case, P were true and Q's not, right? So P turned out to be true, but Q was false. So in that case, the implication would be false. Okay. Okay. What about if P is false, right? What happens then, right? So if P is false, then what happens to our implication? Well, the easiest way to say this is me just to tell you, because this is a little weird. The implication is always true in that case. This may seem a little weird, but once you've used it a little bit, this will make more sense. If you're trying to prove a statement where the if part is false, the what you're assuming to be true, right? The if part is false. The whole sentence is always true, right? So it'd be sort of like this: if 2 is odd, then this class is easy. Okay, that's a true statement because 2 is not odd. So no matter what comes after, the whole thing will be true. Okay? That's what we call something being vacuously true. That's a fancy word, but kind of fun to say. So it's because there's no real meaning to the first part of the if. So if the sky were green, then I will make an A on the next test. Okay? That's a true statement because the if the sky is green part is false, so whatever comes after it will make this a true statement. Again, that's a little weird to get used to, so it may be something to make note of that whenever you have a false P, then the statement P implies Q will always be true. Okay, this needs some examples. So let's say that P is we win today's game, and Q is the statement we go to the World Series. Then P implies Q, that's straightforward enough. You would just say that in English as if we win today's game, then we go to the World Series. Yay, awesome, right? Um, you might say that lots of other ways in English, though. You can think of other ways you might say the same sentence, right? And if we win today's game, we go to the World Series. Well, you could say, just like we did before, if we win today's game, then we go to the World Series. You might say it as um, winning today's game implies that we go to the World Series, so on. So with P's and Q's, it would be like P implies Q. Here's a weirder one, but this also works in English. P happens only if Q happens. Or another way to say this is P is a sufficient condition for Q to happen. So think about this with the game. Winning today's game is sufficient to get us to the World Series. You might also think about this, sort of written the other direction, where P's on the right hand side, Q's on the left hand side, but the arrow still goes from P to Q, right? So it's still the same thing. That's exactly the same sentence, the same statement that we had before. But maybe it makes the following make a little bit more sense. If we think about this from Q's point of view, you might say this as Q is a necessary condition for P. In other words, um, things like Q happens whenever P does. So we will go to the World Series whenever we win today's game, right? Or we will go to the World Series provided that we win today's game. All those are exactly the same thing in English. So why bother with all of this stuff? Well, you'll often read English sentences that you'll have to think about for a second and turn into, you know, a logic statement with wait, what's implying what now? And when you do that, they can make it much easier to see what's really going on. What is that we really want to prove? Oh, it's just that this implies that, even though it was said in some sort of weird way with the way that it was written out in English. So, again, the implication P implies Q using that we win today's game and go to the World Series. If we win today's game, then we go to the World Series. Winning today implies we go to the World Series. Winning today is sufficient for us to go to the World Series. But one bit of warning when you do implications, right? And this is kind of easy to see if with this example. Um, so remember here, P implies Q. We win today's game, we go to the World Series. Okay. The warning is that P implies Q is definitely not the same as Q implies P, right? In other words, the arrow can go in one direction, but not necessarily work in the other direction, right? So, for example, if we win today's game, then we go to the World Series. That's a perfectly good sense. In other words, that may mean that winning today's game means we're in the what National League Championship Series. We've already won 3 games, and so if we win today's game, then we get to go to the World Series. So that P implies Q might be a perfectly true statement. Okay, but we might be able to go to the World Series even if we lost today's game. Suppose that we're in a situation where how do you get to the World Series? You have to win 4 out of the 7 potential divisional or league championship series games. So I'm a big St. Louis Cardinals fan, so we're going to go with the National League. So we're in the National League Championship Series, and say we win the first 3 games, right? Then if we win today's game, right, number 4, then we get to go to the World Series. But we could still lose today's game, right? In fact, we could lose 3 more games as long as we win the last one, right? To make it to win number 4, we will get to go to the World Series. So this is a great example of a situation where P implies Q is not the same as Q implies P, right? In other words, it very well may be that someone could win the first 3 games of the championship series. Say that's where we are, right? Today is the day for game number 4. If we win today's game, then we go to the World Series. That's a perfectly true statement. But it's not true that if we go to the World Series, it's because we won today. Because we could still lose today and go if we win tomorrow's game. So the sort of situation where it does work both ways, where P implies Q, and, again, that's our friend and, right? Conjunction, the little wedge again, and Q implies P, right? So the arrow works in both directions, right? We usually write that, well, with one arrow going in each direction, one arrow with a point in each direction. And we read that as P if and only if Q. And a lot of times we'll write it even shorter as P and then IFFQ because it's if and only if. So it's sort of like IF and then there's you wrote a bunch of other words, then another if, and it's like you just condense all that stuff in the middle with the second F on the last if. So PIFF means if and only if. And again, you might say this also in English as P is a necessary and sufficient condition for Q. So, for example, if we're still using P and Q the same way we were a second ago, then P if and only if Q, right, with the arrow that goes both ways, right? I mean, we go to the World Series if and only if we win today's game, or it is necessary and sufficient that we win today's game in order to go to the World Series, right? That's when it would work both ways. And there'll be times when we want to prove theorems that are something implies something else. And then there'll be times when we want to prove equivalences like this, where we want to prove something if and only if something else. And oftentimes we'll have to do that in two parts. We'll prove one direction, then we'll prove the other direction. Well, to help us along our way as we are doing proofs, something that will be extremely important to keep in mind are various tautologies. So a tautology is a statement that's always true. Here's an example. Remember back the way De Morgan's laws worked, right? That not P or not Q was exactly the same as not P and Q with the P and Q in parentheses. Or the second De Morgan's law, exactly the same thing when we just switch the roles of the ands and the ors. So not P and not Q. That's exactly the same thing as not parentheses P or Q. Okay, so that's a tautology. You could go through and show that that's a tautology by writing out the truth tables, and you would get to a column that was just straight truths. Okay, so here's another example that's maybe more interesting. Um, Not P implies Q. Okay, that turns out to be exactly the same as P and not Q. Okay, um, that's pretty easy to see if you think about this. What does it mean to say that P doesn't imply Q? Right. Well, that would mean that P happens and Q doesn't, right? P's true, but Q's false, right? That's what it really means. So that would mean P's true and Q's false, right? That would be P and not Q, right? So again, maybe just as an exercise in playing with the truth tables again, let's work out the truth tables for this and see what happens. So if I have the truth table for P implies Q, we've done that already. That's true, false, and then true, true at the end. Again, keeping the order the same way so that it makes things easier for us. The negation of that would be, well, we just turn all the trues and falses the other way around. So now the truth table column for not P implies Q looks like false, true, false, false. Okay, okay, let's try P and not Q. Well, how would the truth table for this work? P is true and not Q. So if P is true and Q is true, then the whole and would be false because I'd have true and false. Okay? On the other hand, the second row there gives me a true P and a false Q. So when I take the negation of Q, I get true again. So true and true gives me true in this row. The next row, I'll have false and false, so that becomes false. And the last line becomes false and true, which again is still false. Okay. Wow, okay. So let's go back and slide over the two things next to each other, and you see that they are exactly the same. Right? So one is true if and only if the other is true. Okay. Um, if I wanted to work out the conditionals, right, and work out what it would mean for a truth variable for both of them, I could do that. But to show that one is true if and only if the other is true, you really just have to show that they have the same truth values. And keeping everything nice and organized like this, you see that those columns are exactly the same. So this is going to be extremely important for us in later lectures, because what it means is, suppose I wanted to disprove a an implication. Suppose I wanted to prove that P implies Q was false. Then that's the same as showing that P and not Q, right? That's true. Okay, so that will be really useful for us later as we start going through actually writing proofs and not just going through the building blocks of how we're going to make them. Now, there's a bit more fun we can have with implications. So let's summarize what we've done so far and see one more thing we can do. So if we're looking at an implication, P implies Q, we know its negation, that would be P and not Q. And we talked a bit about its converse, although we didn't call it that a few minutes ago, where instead of looking at P implies Q, you turn the arrow around and you look at Q implies P. And remember, that did not necessarily have any connection to the original one. One could be true, an implication can be true and its converse can be false, and vice versa. But there is something we can do with an implication to turn it into something that's exactly the same truth value wise, and that's take its contrapositive. In other words, if we have P implies Q, we switch that around and make it not Q implies not P. And it turns out that if an implication is true, its contrapositive will be true and vice versa. Okay, this definitely needs an example. So if we go back to our P, we win today's game, Q, we go to the World Series, then the negation of P implies Q would be that we won today's game, but we didn't go to the World Series. That kind of stinks, right? But that would mean that implication was false. The converse would be, if we go to the World Series, it'll be because we won today's game. And remember, we spent some time talking about the fact that that doesn't necessarily have to be true, even if the original was true, and vice versa. But think about what the contrapositive says. The contrapositive says, if we don't go to the World Series, then we didn't win today's game. So, not Q implies not P, right? And that's exactly the same as saying P implies Q, right? Because, let me say the two sentences together. P implies Q would be, if we win today's game, we go to the World Series. The contrapositive of that would be, if we don't go to the World Series, then it's because we didn't win today's game. And you see, that's exactly the same sentence, right? Just rewritten so that one's the contrapositive of the other. So, super and critically important fact here to end our video with. The truth of an implication and its converse are not related at all. But an implication and its converse are equivalent. So one's true if and only if the other one is. You could write that out as a tautology. What that means is, as we'll see in some later videos, if you want to prove an implication, sometimes it's easier to prove its contrapositive.